All right. So before we begin, are there any questions about anything that was covered yesterday or the lecture before? Any questions or any comments? Was the subject matter clear? And is everyone able to access the Google Classroom site without any problems? Or rather, if there are any issues, please feel free to let me know or type it in the chat window. Okay. All right. So if there is no further questions or no questions at all, let me continue our discussion on first order differential equations. Okay. So yesterday someone raised the point, I think in the chat window, that this looks like a linear differential equation. And I promised that that is a subject that we will cover today. And so that is what we will start with today. So today we want to introduce the idea of what is a linear differential, first order differential equation. And then we will develop some methodology to try and solve it. And then we will try and go slightly beyond and see how certain nonlinear equations can in principle be brought to the linear form so that we might use the same tricks and tips. Okay. So we begin by introducing the notion of a linear ODE. Excuse me. The general form of a linear ordinary differential equation is given by y prime, which is dy dx, plus some function of x times y equals some function of x. Okay, so it is linear in both the derivative and the function y. Okay, so note that this form is linear in both y and y prime. Okay, so there is no plus y cubed term here, right? So any differential equation that is given in this form or can be brought into this form is called a linear differential equation. Anything that cannot be brought into this form is called a non-linear differential equation. So as I talked about the general philosophy of these things yesterday, we will be restricting ourselves to solving this class of equations to develop certain solution methodology. And you will actually find that this very closely parallels our discussion yesterday. So you might not need a lot of new things to solve this. So now that the definition of linear is clear, let me try and solve this differential equation or develop a solution assuming some general P of x and R of x. Note that there is no restriction on P of x and R of x. Okay, so there can be any functions of x. They could be x squared, x cubed, sine x, e to the x, whatever it is. There is no restriction of linearity on the functional form of P of x and R of x. So I will first sketch how you would go about solving this using the same techniques developed yesterday. And then I will try and simplify that technique and then try to tell you that there is a much easier way in which you can get the solution by direct integration. So I'll call these methods 1 and 2. Method 1 is basically what we discussed yesterday. I will not do this completely. It can be slightly laborious, but understandably, both methods give you the same answer. So note that this differential equation can be brought into the form that we discussed yesterday. The form that we discussed yesterday was m of x comma y dx plus some function of x and y times dy equals 0, right? So they're all various ways of writing y prime equals f of x, y basically, right? So if I look at the equation written above, which I will call equation 1, equation 1 can be brought into the form of equation 2. The way I would do it is by writing equation 1 as dy dx is r of x minus yp of x, and then rearranging this to look like dx minus dy equals 0. Okay, so this at least form wise looks exactly the same as 2. So now we can make the identification that m of x comma y for this guy is basically r of x minus yp of x. Okay, and n of x comma y for this guy is minus 1. It is a constant. So again, we will ask if this is an exact differential equation. Well, by inspection, we can easily see that this is not an exact differential equation. This is not an exact differential equation because the derivative of this guy with respect to y is basically minus p of x, and this guy is a constant, so the derivative of this guy with respect to x is 0. So p of x is in general not equal to 0. So this in general is not an exact differential equation. Of course, you know how to bring it to an exact form by figuring out if it exists a suitable integrating factor. So we take recourse to both theorem 1 and theorem 2 and see if either of those two cases apply. If either of those two cases apply, we can turn this into an exact differential equation and then go ahead and solve it the way we did it yesterday. So let us see if theorem 1 applies. To understand if theorem 1 applies, let us look at the factor R, which, forgive me, I have to look at the definition again. So it's over here, 1 over q dp dy minus dq dx. 1 over q dp dy minus dq dx. And remember that if this function is only a function of x, then we are in business. Sorry about an abuse of notation. I think for inexact equations, we stuck to the notation p and q. For exact, we stuck to the notation m and n. So my p is r minus yp and my q is minus 1. So substituting these values, you see that 1 over q is minus 1. dp dy is minus of p of x and q is a constant. So this is 0. So this is purely a function of x. So theorem 1 applies. Okay. So since theorem 1 applies, I can find an integrating factor, which is a function of x alone, which is basically exponential r of x dx. And in this case, this r of x turns out to be p of x, which is the coefficient of the y term in the differential equation. So this is basically okay. So to avoid writing integral p of x dx every time, let us develop a shorthand notation. I will call this h, following your textbook. So the integrating factor f is basically e to the h. Okay. So now I can multiply the given differential equation by e to the h to make it an exact differential equation. Make 3 an exact differential equation. The way I would do it, I'll just multiply e to the h throughout. So I will have r of x minus y p of x e to the h dx minus e to the h dy equals 0. Okay. So now I will leave the rest of it as homework for you because this is pretty much exactly what we did yesterday, right? Excuse me. So what you do is first show that this is exact. It has to be exact by construction, but still satisfy yourself that this is exact. Show this is exact. Okay. And then write down the solution as u of x comma y is a constant. The way you figure out u is by looking at du dx, which is basically r of x minus yp of x times e to the h, and du dy, which is equal to minus e to the h. Okay. Since du dy in this case is a little simpler, start with that. Integrate du dy. Get u as a function of y, but that gives you an undetermined function of x. To determine the function of x, differentiate this guy again, use du dx equals m and so on and so forth, and write down the general solution. Okay, so this I leave it to you as homework. So complete this exercise. So I will admit that this can be a little laborious in this particular case, but it is still useful for you to understand how it works in practice. So please do take it seriously and complete this exercise. Are there any questions about this part? Any questions or any comments? So is everyone comfortable with solving this differential equation on their own? Okay. So if you are, I will move on to an easier way of finding the solution for this equation. Okay. I'm calling this method 2, but these two methods are exactly the same in the sense that we have to find an integrating factor in this case also, but I will show you how you can go ahead and integrate this directly. That is the only difference. So let us start by writing the most general form of a linear first order differential equation again. Okay. So by the way, in physics or engineering applications, R of x is some input that is fed into the system, right? And Y is how the system responds, right? So for example, if you're stretching a string or plucking a string, Y can represent the amplitude and R can represent the force that is acting on the string. Or it can be an electrical circuit and R could be the external input and Y could be the measured current or whatever it is, right? So these things can apply to, for example, in general LC circuits and stuff like that. So you would see, I'm sure you have already seen examples of this in your high school, but it is still useful to keep in mind that these things do occur in practice. Okay, so how do you solve this without having to do multiple integrations and stuff? Again, we had to find an integrating factor. So let us assume that such an integrating factor exists. So I'll call this integrating factor as f, and I'll multiply this equation by f. Fy prime, excuse me, plus pfy equals fr. Okay, it has to be understood that p and r are functions of x alone. Now I can actually solve it by direct integration if my left-hand side is a perfect differential. Okay, so if the left-hand side can be written as d of something, then this can be readily integrated. So what do I mean? Let us say that you are interested in d dx of something like fy, because the first term suggests that fy prime can be at least one part of d dx of fy is already there. So let us see if the other part can also exist. So by chain rule, of course, this is fy prime, the first term, plus y f prime. So if the integrating factor is such that I can turn the left-hand side into a perfect differential, the way I would do it is I will demand, look, f is completely arbitrary at this point. I will fix f by demanding that the choice of f turns the left-hand side into d dx of f times y. Okay, so I'll write this down explicitly. Fix f by demanding that the choice of f turns the LHS into d dx of f times y. Of course, that is a job of an integrating factor. It is supposed to make the differential equation easily integrable. Okay, so which means that the term pf times y should be equal to y times f prime. This is the condition that f should satisfy in order that the left-hand side be called as d dx of f times y. Okay, and since this has to be true for all values of y, I can turn this into an equation for f alone. pf equals f prime. Okay, or I can turn this around by saying df over f is p dx, which implies, of course, as before, that f of x is integral p of x dx. Okay, so this is exactly what we mean by an integrating factor. It helps us to turn the solution of an ODE into something that can be trivially integrated. Well, assuming that the functions that we're dealing with are stuff that can be trivially integrated.
Sir,
Yes.
exponential you haven't written.
Exponential. Oh, thank you very much. Thanks. exponential p of x dx. Yes. So again, I will use the exact same notation and I'll call this h, where h is integral p of x dx. I do not know what p of x is because I'm keeping everything fairly general. So I'll keep I'll keep the notation here also fairly general and call this some h. Any questions so far? Any objections? Okay. So now what remains is basically to feed this into the differential equation and solve it. So by construction, the left-hand side is now d dx of e to the h times y. And the right-hand side is, of course, f times r. So the differential equation is d dx of fy, excuse me, equals f times r. So plugging in the corresponding form of h that we have, this is d dx of e to the h y equals e to the h r. Okay. And now I can easily integrate this because I can turn this around and say this is d of this guy equals e to the h r dx. And integrating this would give me e to the h times y equals integral r e to the h dx plus some constant. Some constant that is independent of x. Okay. So if you carried this through this exercise, you would actually get the exact same answer as this. So somebody told me some constant after integration. I don't know which constant you are referring
Sir,
to.
where df by f is equal to pdx.
So here, so any
Yes.
constant that remains, if it is truly a constant, I can always absorb it in the final C, right? Because this is an undetermined constant anyway. Because a constant is, if it is not if it is a multiplicative constant, let us say you're saying f is just some constant times e to the h, then that constant drops out in this differential equation, right? If the constant is additive, then I can absorb it in this C. So either way, since I'm keeping this C completely general, it doesn't matter. I don't have to put in a constant at this stage. Do you agree? So basically, if let us say there is some constant K, right?
Yes.
That would, if I put in the constant K, so I can write this constant as some logarithm, right? And I can absorb it as K times e to the h, right? Okay, so I'll do this explicitly. Log f equals integral p dx plus some log k, right? Which means, sorry, please mute yourself if you don't want to ask any questions. So log of f over k would be integral p dx. So f would be some constant times e to the p dx. So this is what you mean, right? If I actually solve it properly. But this constant will drop out of this differential equation. Okay, so that is what I mean. Now, if this equation was such that this was not an exponential, but I end up with an additive constant, then that would actually make this equation a little problematic because I'll get an offending term. But since this is an exponential, I can always write this as a multiplicative constant. So this differential equation is unaffected. Okay. Make sense?
Yes.
So yeah, my point about additive constants, what's wrong? If there is an additive constant, then this differential equation would have an extra term. So that would not make it easily integrable. That would be a problem. Okay. So now it turns out that I don't just have u of x comma y equal to c, an implicit solution. I can actually write down an explicit solution by just multiplying this equation by e to the minus h. So y is e to the minus h. Let me write this more clearly. R e to the h dx plus c e to the minus h. Okay. Now, when you multiply through, please be careful. There is an e to the minus h outside the integration. This e to the h is inside the integration. So they should not cancel or anything. So you should first figure this integration out and then multiply through by e to the minus h. But anyway, this is the most general solution for this particular linear first order ODE. And again, forgive me for belaboring this point. I invite you to do it using the laborious method, figuring out, integrating this, figuring out, and showing that this is exactly the same as this boxed equation. Okay. So regardless of which one you want to follow, this is the most general solution. So from now on, if you see if you see a differential equation of this form, then in some region of xy where p of x and r of x are all properly well behaved and integrable and all those things, figure out h, right? Which means figure out integral p of x dx and plug it in this equation and write down the solution straight away. Okay. Any questions or any comments? Okay. So now we'll switch gears, but only very slightly, and we will talk about an interesting differential equation. Okay. This differential equation is dy dt equals ay minus by square. Now, on the face of it, this doesn't look very linear because there is a y square term. Linear means I cannot have powers of derivative or y more than one, right? So this obviously has a quadratic dependence on y. So we would probably be forced to conclude that this is not a linear equation. But it turns out that that is a little hasty, and we can actually convert this into a linear form by a change of variables. Okay. So this change of variables is a very useful trick to develop in the solving of differential equations, because things that look very complex with proper change of variables can actually look very simple. Okay. So for example, maybe I'll just, as an aside, okay, consider something like, for example, let us say x y prime plus y, okay, equals some complicated function like sine of xy or e to the xy. Now this looks a little difficult to solve, right? Because you have e to the x times y, and x and y are married together in a form that is not extractable easily, and you would actually think that this might require a lot of different techniques and so on and so forth. But if you simply use, for example, say some t equals x times y, okay, that's pretty much it. If you use t equals x times y, this differential equation, the left hand side is basically t prime, right? Because t prime is xy prime plus y. So this differential equation can be written as t prime equals e to the t, which is trivial to solve. So these change of variables can come in very handy at certain times when things look very difficult. I'm not saying there's always a possibility, but there is some possibility that there is in the shadows lurking a simple change of variables that might make your life a little easier. But before we talk about change of variables for this equation, I want to talk a little bit about this equation because it's an interesting equation. And this equation was written down in the context of population dynamics a long time ago. And I invite you to study, read up about it. I'm sure there is lots of accounts on the internet about this population dynamics. So what does this mean, and what does this have to do with population, right? So let us say that y represents the population of a system at a population of a species at any instant of time t. Okay. So the goal of this differential equation is to tell you how the population grows or declines, y as a function of time. So what do these different terms represent? So suppose if this b is not there, right? And if my differential equation is dy dt equals ay. Okay? So just to be even more precise, let's assume that we human beings found a new small continent somewhere in Indian Ocean, right? And people are going there and settling down. And this continent has enough resources. It has lots of water, lots of fruits and vegetables and livestock and what have you to sustain people. Okay, so there is enough resources. Hopefully no internet and no Zoom classes, but there is enough resources for you to live, let us say. And people are going there and settling. Okay, the question is, if everything else is equal, how does the population in this particular island grow? If this B term is not there, then the population just keeps growing unchecked, right? Because I'll assume that A and B are both real positive constants. Okay. So if A and B are both positive, and if I take B to be non-zero, sorry, if I take B to be zero initially, and if only A is there, then this Y grows exponentially, right? It's a very easy integration to perform. Obviously, such a thing is practically not sustainable, but mathematically, it is certainly a valid solution. So then what does this B represent? B represents some competition between the different members of the species for resources. So of course, I cannot just put B equals B times Y, because that will still be a trivial differential equation with only one constant that I have to solve. But having a B times Y square, again, I remind you, these are models, right? So there's no exact science here. So you write down a model, you test the predictions of the model and see if the model works in certain spheres. This is, of course, a very simplistic first order model about population dynamics. So B represents competition between the people, right? So if there is lots of competition, then what happens as the population keeps growing, right? So as more and more people keep settling, the competition becomes more and more between the people, because Y keeps increasing with time. And at some point, if B is large enough, and if Y is large enough, the Y square term starts dominating the AY, because if Y is large enough and B is comparable to A or more than A, then of course, the rate of growth is going to fall. And that is understandable, because there is more people, there is more competition, and you cannot really sustain more and more increase because there is limited resources. So, for example, if when something like America was first discovered, dy dt equals ay would have been a very good model, because we have a huge land mass that had vast resources and very little population. So the population in principle could be growing exponentially, but after a certain point, of course, then you have to put in regulations, because there is less resources, right? So this was true for pretty much every country at some point in history. So if I rewrite this differential equation as dy dt equals ay times 1 minus b over a times y. Okay. Now, first of all, notice that this equation admits solutions with dy dt equal to 0. Okay, this is the first point. Admits solutions with dy dt equal to 0, where the growth is basically 0. There is nobody dying, nobody being born, and nobody coming in, and nobody leaving. Okay, this is a very idealistic situation, but these are what are called equilibrium solutions. And the corresponding point, the corresponding values of y at which this happens are called critical points. Okay. So the critical points of this equation are, of course, y equal to 0 and y equals a over b. In both these situations, dy dt in the above equation becomes equal to 0. Okay. Now, critical points can be stable critical points or unstable critical points. Stable critical points simply means that as time increases, the equilibrium solutions stay in equilibrium. If not, they change. The second point to note is that the competition that I was talking about is now more apparent. So since I have factored out the ay term, I have to compare 1 with b over ay to check if the population is growing or falling. So remember that now if y is less than b over a, if y is less than b over a, then the quantity 1 minus b over a times y is always a positive quantity. And so the population keeps rising. So this is the initial growth spurt in the population or in the settlement of a particular landmass. But at some point, as the population keeps growing, because b and a are fixed, remember, I don't keep changing b over a. That will be a very bad model. So once you fix B over A, you have to understand the dynamics for these fixed constants, and you have to fix the constants carefully, judiciously. But if Y becomes greater than B over A, then growth declines. Okay. So without actually solving the differential equation, let us try to understand how this thing is going to look like. So basically, as time goes to infinity, what should be the population? Well, as time goes to infinity, the population is certainly not going to go down to zero, right? Initially, the population is going to rise exponentially. Then after a certain point, when Y is large enough such that the minus by squared term dominates, it's not going to force any further growth. So the population is going to tap out at some value. So without solving the differential equation, I guess that the solution is going to look something like this. So it's going to initially rise a little bit, quite fast, but after some time, it's going to slow down, and then it's going to asymptote to some value. Okay. This seems like a reasonable guess. Do you guys agree or no?
Sir, so shouldn't the population growth stop at the point where 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 dy by dx is 0? After that, it shouldn't grow further. Means that should be the tapering point, right? The saturation level.
Exactly. So what is this? What is this point? This fixes your value of Y, right? See, the dy by dt, as we discussed, has 2 points at which it can be 0, right? Y equal to 0. Now, that is a trivial point, right? The population doesn't tap out at Y equal to 0. So the population taps out at A over B in this particular model. Yeah, you're absolutely right. So I started at time t equal to 0, right? So suppose if I forget all this population dynamics or all this physical interpretation, I can keep extending this function. And I can actually extend this function and write it this way. Okay, but I won't because I want to stop, because I want to interpret this as corresponding to some physical system. Okay, so let us actually try and see if our guess is sort of borne out by this solving of this differential equation. So let us go back to the differential equation. Dy dt equals ay minus by squared, which again, as I told you, doesn't look very linear. But suppose if I make a change of variables, u equals 1 over y. Okay. Then obviously du dt is minus 1 over y square dy dt. So dy dt can be written as minus 1 over u square du dt. Okay. So substitute this in this equation. So dy dt on the left hand side, I will substitute by minus 1 over u square du dt. And y is obviously 1 over u. So this is a over u and b over u square. Multiply through by minus u square and you get du dt equals b minus au, which I can easily rearrange to write du dt plus au equals b. And this is a special case of a linear differential equation, y prime plus p of x, y equals r of x, with p of x equals a constant, and r of x equals b, a constant. Okay. So even though the equation doesn't look very linear, by a change of variables, I was able to get to a linear form. Now, since I know the solution for this particular differential equation, y of x equals e to the minus h integral, what is this? I hope my memory improves. R e to the h dx plus c e to the minus h. So h was, of course, p of x dx. And in this case, p of x is just a, and dx is just the variable is t and not x. So in our case, h is integral a dt, which is just a times t. So substitute everything and you get the solution as u of t equals e to the minus at integral r, which is b, e to the h, which is e to the at, dx in our case is dt, plus c e to the minus at. Okay. So this integration is trivial. E to the at is just e to the at over a, and e to the at and e to the minus at cancels. The first term is basically b over a. The second term is c times e to the minus at. Okay. So by the way, the most general solution, this guy, right, it can be interpreted as the first term has r, right? Remember that we talked about r as the input. The second term does not have r. So the combined response of the system y can be written as a response to the input r plus the response to whatever was there initially, the initial data. Okay, so these two terms can be interpreted physically or in your engineering problems as the first term corresponding to the response to the input that you provide, and the second term as corresponding to the response to the initial data. Okay. So be that as it may, for our simple equation, which is dy dt is ay minus by squared, we have figured out the most general solution. Of course, we are not determining C. I just wanted to write down the solution. And now let me write down y. So y is, of course, 1 over u, right? So this would be equal to 1 over b over a plus c e to the minus at. So multiply the top and bottom by e to the at to write it in a slightly different fashion. You can leave it as such, no problem. But this can be written as e to the at divided by constant plus b over a e to the at. Okay. So now, if this was an initial value problem, right? So if I told you that at time t equal to 0, the number of settlers was 5, then you can use that to determine C in terms of the given constants B and A. Okay. So that is point number 1. Point number 2 is, let us see if it has the right asymptotic value. So as t goes to infinity, what happens to this? Y of t goes to e to the at. Now, whatever be the value of c, it cannot compete with e to the a times infinity. So this is b over a times e to the at, which means the population goes to a constant value, which is a over b. Okay, so which is what our common sense graph also told us. I should have written all this in green because this was an example and I forgot. But anyway, it doesn't matter. So the point in this lesson is that there are equations that don't look very linear that can be brought into a linear form. So all this belaboring was for that, but I thought this might interest some people because it's actually a cute differential equation. So the question is, are there others that look like this?
So why did the C disappear when we took t tends to infinity?
So look at this equation, right? So when t goes to very large numbers, the exponential dominates, right? Because I already told you that capital A and capital B are positive constants, right? So no matter what the number c is, e to the something times infinity is very, very large. Exponential grows much faster than any other term, right? So as I keep increasing time, this term keeps growing larger and larger. So this term basically C can be neglected compared to this term in the asymptotic limit. Does that make sense?
Yes, sir. Thanks.
Okay. Any other questions or comments? Anybody? Okay. So the question is, are there others that can also be brought into a linear form? And
Hello, sir.
Yes.
Sir, can you explain the graph which is given in the book?
Which graph?
This equations graph.
This one right here?
Above a by b. Yes, sir. Above a by b, some graph is given. Can you explain that?
which I just drew one plot. I
No,
don't-
sir, in the book. In the book.
in the book. I don't have the book with me. Just a second. Okay. Figure 21 in the book. Yes, that's what you mean. Hello.
Yeah.
So the point is, if I start with a very low population, my population keeps growing till it taps out at A over B, right? Now the point is, what if I start, so what if I transport, let us say 1 billion people into this, right? Then people keep fighting amongst themselves for the resources and either leave or die till the population taps out at A over B. So regardless of where you start, whether you start with a very low number of people initially or whether a large number of people initially, the population is going to tap out at some constant value asymptotically. That is the point. Okay, this is the physical explanation of the graph. So basically what happens, I assumed the way I interpreted this graph was to say that initially y is not a large value, which means A is helping the population grow and at some point B takes over. But I can actually turn this around and say, what if the initial value y of 0 is 2 billion? In that case, of course, A is completely negligible. The A term is completely negligible compared to the B term, right? Because the by square is going to dominate because you're starting with a population that is very, very large, which means there is no chance of growth. And the only thing that is going to happen is decay. Does it make sense? Since you're starting with a very large population, if you start with a very large population, the A term doesn't really play much of a role. And the B term is the one that is going to dominate for the entire range, and the population is going to start at 2 billion and then keep falling till it reaches A over B. That is how we interpret the graph. Make sense?
Yes, sir.
Okay. So yeah, so for completeness, I should also give you that picture, even though I did not. Good, thank you. So there is a class of equations, and this goes by the name of Bernoulli equation, which can be written in the form y prime plus p of xy equals g of x times some y to the a. Okay. Oh, sorry. Okay. So y prime plus p of x times y equals g of x times y to the a. Now, of course, if a equal to 0 or 1, the Bernoulli equation is already linear, right? If it y is a is 0, then it is already linear because it is just g of x. And if a is 1, then I can club the y term along with the p of x term, and it is of the form y prime plus some k of x times y equals 0. For some other value of a, this equation doesn't look very linear written in this particular form, but it turns out that you can actually make it into a linear form by the following transformation. So the population dynamics example was one example of this particular transformation. The general transformation is you write u of x as y of x to the power 1 minus a. Okay. In our previous example, a was 2, right? Because I had a y square term. Remember this guy. Okay. So which means my transformation was u equals y to the 1 minus 2, which is 1 over y. So in general, if I have some a, my transformation that I should employ to make this linear is y to the 1 minus a. So we can trivially check that works because u prime is given by 1 minus a, y to the 1 minus a, which is y to the minus a times y prime. Okay, so this is my u prime in terms of y prime. But of course, I know what my y prime is from this equation. Y prime is obviously g y of a, y to the a minus p times y. So let us substitute that here. So this is 1 minus a y to the minus a times g times y of a minus p times y, where g and p are functions of x. So I'm just writing it as g and p for brevity. So this is obviously equal to, the first term is g times 1 minus a, and the second term is p times 1 minus a times y to the 1 minus a, which is precisely u. So I can rewrite this differential equation as u plus 1 minus a p of x u equals 1 minus a g of x, which is a linear first order differential equation. So equations of this form can be brought into a linear form by this particular transformation. So we just worked out an example where this was shown to be explicitly true. And I'm sure you will work out other examples in your tutorial. So before I close for today, let me say a few words about the last topic, which is really an application of ODEs. And this has to do with what are called orthogonal trajectories. Okay. What are orthogonal trajectories? So let us take a familiar example from physics, which is electrostatic lines of force and potential. Right? So you know that the field E in general is given by minus del V, right? Because it's a conservative force, electric field can be written as a gradient of a potential. But since I'm dealing with one dimension here, let me write E equals minus dV dx. Okay. So which means that dV dx, since it is tangential, the curves of the electric lines of force and the equipotential surfaces will intersect at right angles to each other. Okay, so suppose if I have a realistic situation or a semi-realistic situation, I don't know, where I generate some kind of an electrostatic field and I draw the electric lines of force and the equipotential surfaces in the same region, and I ask how do they cross? How do they intersect each other? It turns out that they will intersect at right angles. So this in general can be turned into a mathematical problem of stating as follows. Suppose you have two curves or two families of curves. Okay. Or let me state it slightly different. Suppose if we have, suppose if we have a curve or a family of curves. Okay. What are the curves that are perpendicular or orthogonal to the first set? Okay. So how do I determine this? So first of all, I should understand what do I mean by two curves being perpendicular. I can understand two lines being perpendicular, but suppose if I have a curve like this and a curve like this, right? So what is it that I mean when I say that they are perpendicular or whatever it is? The way I should first understand this is I should first draw tangents to both these curves, right? So let us say I have this curve. Now let us say that I want to draw the tangent to this curve. So they should intersect at some point. So I'll draw the tangent to this curve at that point, and I'll draw the tangent to this curve at that point. And the angle between the curves is basically the angle between the tangents to the curves. Does this make sense? This is how the angle, sorry about the really crappy diagram, but I hope you understand the point. Suppose if the two curves intersect at some point, then the angle between the curves at that particular point is basically the angle between the tangents to the curves at that point. Okay. So even if you don't understand the diagram, I think the definition is quite clear. And I'm sure you have seen this in your calculus. You can actually write down a formula for tan phi in terms of the slope. So suppose if the slope is m1 and m2, then tan phi is some function like m1 plus m2 divided by 1 plus m1 m2 or something like that. And the condition for orthogonality basically is that the product of these two slopes has to be -1. Okay, so I think the formula is this m1 m2. You can actually verify if I'm correct. Okay, so if phi has to be 90 degree, the left hand side should blow up because tan 90 is infinity, which means the right hand side should be divided by 0, which tells me that m1 m2 has to be -1. So the product of the slopes of these guys should be -1. So what does all of this have to do with differential equations? So do you have a class after this? Anybody?
Yes, sir.
Yes, sir.
Okay, I'll try to wrap up. So suppose if I'm giving you one set of curves, let us say, I'll take the same example in your book, right? So the example in your book is y of x equals, sorry, x square over 2 plus y square is some c. Okay, this is a family of ellipses, right? It's a family of ellipses because if I told you instead that this is equal to 1, then this is one ellipse with some semi-major axis and semi-minor axis. But since I'm letting the right hand side to be a free parameter, I can choose any value of c and this becomes a corresponding ellipse. So this is a one parameter family of ellipses. So the question is, what are the curves that are orthogonal to these guys? Okay. Well, the first step is to turn this into a differential equation. How do we turn this into a differential equation? Well, simply differentiate. So if I differentiate this guy with respect to x, I get x plus 2y y prime equals 0, which tells me that the slope of these guys at any particular point y and x is given by y prime equals minus x over 2y. Now from calculus, I know that the slope of the other guy at the point has to be such that that slope times this slope has to be -1. So I know that the slope of the orthogonal trajectory is such that I'll call this some y prime tilde should satisfy is, so if the product of these two guys has to be -1, then there is already a minus sign here. So this guy has to be basically the inverse of this guy, right, at that particular point. So I will write this as 2y tilde over x. Okay, now why y tilde and not x tilde? Well, x is a dependent variable and I'm writing both of them in the xy plane, and I have to differentiate between the y's because these are two different functions of x. Okay, so I can simply guess what the slope is by appealing to this familiar result from calculus, and then I can turn this into a differential equation by simply I can simply solve this differential equation by integrating to get the family of curves. So in this case, for example, dy tilde by y tilde would be 2 dx over x, which I can integrate trivially to find y tilde is c times x squared. So which means if I'm given a set of ellipses, then the family of curves that are orthogonal trajectories of these ellipses are basically parabolas. Okay, so these are parabolas. So the way you figure out orthogonal trajectories is figure out the slope of the first guy by differentiating the equation to the curve, and then figure out what the slope of the orthogonal trajectory is, and then simply solve that first order differential equation to get the functional form of the second guy, and that will give you what the second set of curves are that are orthogonal to the first set of curves. Okay.